All right, welcome to today's lecture. We'll continue with the operations research course. In this lecture, we shall introduce a new terminology called post-optimality analysis. So we shall look at usually what we do when we get our optimal solution or when we want to get more understanding to the optimal solution, right, or to the linear programming problem. So the post-optimality analysis, we'll look at introduction to it. Then we'll look at the term called duality. That is how to interpret the primer economically, how to also economically interpret a dual form. So we have a primer form of the problem and we have a dual form of the problem. Then there are some exceptions to the primer dual relationship. We shall look at that. Then we will look at what we call sensitivity analysis. That is, we conduct sensitivity on analysis on the linear programming problem based on the established optimal solution or strategy that we've obtained. We shall see if there are changes in the right-hand side values. Remember, the right-hand side values are the resources, assuming you are producing something with limited resource, you know that your stock, you have an amount of limited resource. However, you go to the warehouse and the resources has changed. What will you do? So that's what we want to do. Then look at changes in the objective function, assuming the coefficient in the objective function is changing. How do we handle that? How do we handle that? The information given to you by the third party has changed. So you needed the cost of, let's say, any material, or you want to sell your product at a particular charge. However, you go to the market and due to external factors, the value has changed. How does it affect your optimal solution? Do you need to rework the whole thing? We'll look at that. Then finally, we shall employ sensitivity. We shall employ computer solutions in handling linear programming problems. We talk about the variables. When it's more than 2, you cannot solve using the graphical method. However, the simplest method may be más complex, may be más confusing, especially if you have more variables like 5, 6, 10. Sometimes you can have about 1 million variables. So how do you solve them using computer strength? So we shall use, we'll introduce ourselves to 1 or 2 computing applications, so we can solve the linear programming problems. All right, so let's look at what we have. So it is often possible that further analysis of the optimal solution will result in more useful information than is actually given by the actual solution. So the analysis of the optimal solution for additional information is referred to as post-optimality analysis. So remember, we have optimality, right? So post-optimality is what we are doing after obtaining the optimal solution, right? So in this case, the optimal solution of a linear programming model can be analyzed in 2 ways. What are they? 1, the dual can be formulated to obtain useful information regarding the value of the resources that form the constraints of the model. Then also the various numerical coefficients in the model, constraints, and also in the objective function can be analyzed. So we can see their sensitivity to changes in, in case they change, how would they impact or influence the optimal solution? So we'll see that both the duality. So the dual form and the sensitivity analysis are used to investigate the optimal solution to gain additional weight. So the post-optimality analysis are actually done in two ways: the dual form or duality, and also sensitivity analysis. All right, so what is duality? So every linear programming model has two forms. So every model that we have talked about have two forms. The first one is the primer, and then the dual. So the primer is actually the first or original form of the model. So the original form of the model, as we've been using, or we've been um, formulating and then solving, is referred to as a primer, right? However, every dual is the second form of the problem. Dual is the second form of force. What we say is that every primer solution, there exists a corresponding dual solution, right? So we can always create a second form of the problem and also solve it. And that's also referred to as the dual solution, right? And when that is done, you see that we analyze the dual for one or both of the following reasons. One, to provide economic interpretation of the resource materials or the resource parameters of an LP problem, and occasionally it can be easier to solve the dual form of the model than the primal form. Sometimes it's difficult to solve the primal form, right? But easier to form the dual. So we can form this dual, solve it, and use that understanding to solve the primer, right? And we shall see this. Those who want to advance more, there is a dimensionality aspect of this research, or in linear programming, and dual is a good form of solving such challenges, right? Okay, so let's consider this problem. So a firm manufactures two products, product 1 and 2. The production of product 1 and 2 is subject to the following resource constraints. So resources, so we need 1 hour for product 1 and 2 hours for product 2, and a total resource available is 10, right? Then we have 6 kilogram per unit for product 1, 6 kilogram per unit for product 2. Total available is 36, and the storage space for product 1 is 8 meters square, and that of product 1 is 4. And the total space available is 40 meters square, so given the profit per unit of product 1 and 2, that product 1 is $4 and product 2 is 5. We have to formulate this model. So this is easy. At this stage, we should be familiar with this, right? So you can see that you want to maximize a function called 4x1 plus 5x2, and that function is subject to x1 plus 2x2 less than or equal to 100, 6x1 plus 6x2 less than or equal to 36, then 8x1 plus 4x2 less than or equal to 40. And all these satisfy the non-negativity rule, right? So we can create from the simplest method. We know all this already, right? But let's see that if this is when we solve this particular problem, we arrive at this optimal tableau or this optimal solution, right? Right. So the Z is actually 28, and x2 we need to produce 4, x1 we need to produce 2, and there is a surplus space of 8. So let's see the understanding of this. So when we observe the Cj minus Zj values under S1 and S2, right, it can be seen that if S1 and S2 enter the basic, profit will increase by 1% and 0.5% respectively. So you can see this, right? when we force to let S1 enter into the solution, right? We force to say that let's S1, let's create an in here and find out an out here, right? To replace any of these basic solution, right? Or the basic variables or the variables in the basic solution, right? Because it's -1, it's going to reduce, right? It's going to reduce our profits. We assume you are dealing with profits, right? So it's going to reduce our objective function, right? Oh, yeah, it's going to reduce our objective function by 1 unit because it's -1, right? And similarly, if S2 enters a solution, it will reduce the objective function by half of a unit, right? Half of a unit, which is, let's say the unit is, let's say $0.5, and this one too is $1, right? So you see that since S1 and S2 are not in the basis, right? Both labor and material resources are fully utilized, right? So S1 is here, S2 is here, right? So since they are not in the solution basis, it means that both labor and material are fully utilized. However, we have S2, we have X3, a surplus of 8. You see, space left, right? So it means that if S1 enters the basis, it is analogous to a reduction in the use of labor by 1 unit. So if S1 goes into solution, it means that we are reducing the usage of labor by 1 unit, right? So assuming that one of your labor is not coming to work, then it means that you know the impact of introducing 1 labor into the solution base. It's going to reduce the profit, which is 28 by 1, by $1, right? So if 2 labor, 2 of your workforce do not come to work, there's going to reduce it by 2 in that order, right? So similarly, when you deal with S2, which is the material, right, you force it into solution, it will also result in a reduction of 1 unit of the material, okay? 1 unit of the material. So if the entry of 1 unit of the slack variable S1 will result in profit by $1, will reduce the profit by $1, then it means that if we want to increase the labor, assuming we want to consciously increase the labor by 1 unit, then it means that we may be increasing the profit by $1, right? So does it worth it? If I'm paying a labor 20 cents, right? Then it means that if I should employ 1 more person and I'm incurring a cost of 0.2, right, to get a profit of 1, then it means that my net profit will be 80 cents. Does it worth to do that, right? So that's what duality is teaching us, right? Again, if S2, which is the material resources, we try to decrease, we try to force this material S2, we try to increase the material resource by 1 unit, then it means that we may be increasing the profit by this margin, 50 cents, right? So you can see that the $1 and the 50 cents, therefore, are the marginal values of labor and also the marginal values of material, right? So in other words, we could expect profit to increase by $1 or 50 cents if another unit of labor or material, respectively, can be obtained, right? So you see that the CJ minus ZJ value under the slack variables that is these values, right, under the slack variables, are normally called the shadow prices. We call them the shadow prices, right, or the marginal values. We call them the shadow prices or the marginal values. So they are actually the maximum prices one is willing to pay to obtain more of the resources in order to maximize the profit, right? In order to maximize the profit. So the CJ minus ZJ value for S1, which is -1 for labor, and for S2, which is -0.5, right, for material, and that of S3, which is there because it's in solution basis, right? It is seen that this CJ value for S3, which is 0, implying that storage space has no value on marginal basis, right? What it means is that storage is not a binding constraint because we have excess of 8, right? There is an excess of 8 meters squared, right? So it is not a binding constraint, right? Because it is in the solution basis with a value of 8, which implies that 8 meters square, right, is left unused, right? So then how do we formulate the dual form of the LP model? So let's look at the formulation. So the dual form of LP model is that for a linear programming model, which is a maximization problem, right, which is primal, its corresponding dual form is the opposite of maximization, which is minimization, right? So the maximization is primal and minimization becomes the dual, right? Great. Now, a primal minimization obviously will also be a dual maximization. So assuming we want to generate the dual form of this model, right? We want to create a dual form of this model, right? So it will be a minimization problem, right? It will be a minimization problem. And this is how we'll see. So it's a minimize Z, then we'll put D here, indicating that it's the dual form, right? Not the original problem, right? And the BIs, the resources, become the coefficients in the objective function of the dual. So we'll have 10 yi, so let's say 10y1, plus 36y2 plus 40y3. That is the objective function. So we use the 10, 36, and the 40, right? And what are the constraints? So this is y1, y2, y3, something sort of, right? So we have x1, x1, x1 here, right? So all these becomes our y1, right? Then we have that becoming our y2. Okay, yeah, we have that becoming our y2. So this is how we create it. So it will be y1 plus 6y2 plus 8y3, right? Then, because it's minimization, remember, you put the original problem into the standard form of a linear programming, right? Or the original formulation standard, or the standard way of representing a maximization problem, right? So when you say maximization all the constraints are less than or equal to, right? So that the dual form will then follow as greater than or equal to, and it is the 4 here, right? That's the objective function. So the CIs and the BIs, they interchange when you are creating the dual. Then the second constraint will be 2y1 plus 6y2 plus 4y3, right? 4y3. Okay, so I should rather use this box as constraint 1 and constraint 2 and maintain my y's. So let me maintain my y's here as y1, y2, y3. So constraint 1 and that of constraint 2 is that. So this highlighted is constraint 1 and this is constraint 2, right? So constraint 1, x1 becomes y1, 6x1 becomes 6y2, and that's it, right? And this is also greater than or equal to 5. And now we have created 3 variables out of the 2, right? And we'll say that they also satisfy the non-negativity rule, right? Good. So you see that the y i's that we have created. So these y1, y2, they are like the yi's, right? They are the marginal values. They are the ones which are in the CJ minus the ZJ areas, right? The marginal values. So now we are going to solve for the marginal value of 1 unit of the resource, right? So I is the 1 unit of the resource in the first constraints for the original primer, 1 unit of the resource in the second constraint for the original primer, and so on, right? So y1 is the marginal value of a unit of labor, and y2 is the marginal value of a unit of material, right? Especially in this resource. And the y3 is the original value for storage. So this is the same problem we're looking at, and that one was for labor, this one was for material, and we also have this for storage. All right, so that is the duality. So let's interpret the duality. So the relationship between the primer and the dual formulation can be summarized as 1. The maximization of a primer becomes a dual minimization. The dual variables y1, y2, y3 corresponds to resource constraints in the primer model or the problem. Now, the number of resource constraints in the primer equals the number of dual variables. The right-hand side parameter, which is the BI, in the primer corresponds to the coefficients of the objective function in the dual, and it's also vice versa, right? Then the AI, the activities, the AIJ coefficient in the primer are the AGI values in the dual, right? So they interchanged, but on the vertical or in the constraint section or in the constraint row, right, of the primer becomes AGI, AGI. So the AIJs becomes AGI, right? Then the CJ values in the optimal in the primer are the right-hand side values in the dual, right? Then all constraints in the maximization primer are less than or equal to, and all constraints in the minimization are greater than or equal to, right? So in general, we can represent the general form of the primer as we want to maximize a function, right, which is summation of j from 1 to n and cjxj, right, and has the following constraints: a, aij xj is less than or equal to the bi's, where I is 1 to m, right? And already j is 1 to n, right? And xj is greater than or equal to 0, then non-negative 2. So the dual form is, we want to minimize, it was maximization z, so we want to minimize z, right? And the bi's become the coefficients, and the coefficients become, the primer become the bi's, right? The aij then becomes aji, right? And the number of constraints in the primer becomes a number of marginal values in the, or decision variables for the marginal values in the dual form, right? And similarly, the marginal values should respect the non-negativity constraints, right? They have to satisfy non-negativity constraints. So algebraically, right, we'll see that the primer is max z cx ax less than or equal to b, right? And the corresponding dual is the minimum mean zd, right? It's equal to yb, and is subject to ya greater than or equal to c, right? And y is also greater than or equal to 0. So if we are to look at this, so yeah, where A is an mn matrix, B is an a column vector, and C is a row vector, right? Y is a row vector, right? So you will see this more when we are using the computing applications in solving linear programming, or when you are formulating, formulating a large linear programming problems, right? Then you see the essence of coding these matrices so that you can be able to solve them, right? All right, so this is the common interpretation of the dual form. So in the dual form, right, the primer max z, right, becomes a mean z d, right? Max z become a mean z, and it actually works in the form of when the constraints are 3 here, right? And now this constraint becomes 2, right? And the coefficients in the dual becomes 3, and that's in the primer becomes 2, and C variables become 3, and that becomes 2, right? Okay, so if we are to solve the primer, so this is the initial solution. When we saw the primer, we had 28 and -1, -half, right? Coming in here, all right. Then when you solve the optimal, when you solve the dual problem, right? The optimal solution is still, the z is still 28, right? However, you see the 1 and the half coming to solution, and the 8, 2, and -4, 8, 2, 4 are actually the marginal values here, right? They're actually the marginal values here. So you see that from the two tableau, right? The negative CJ, ZJ under the S1 and also under the S2 of the primer correspond to the solution values of Y1 and Y2 of the dual, right? Y1 and Y2 of the dual. Again, considering the CJ, ZJ values in the primer solution, right? We'll see that X1 is 2, right? However, X1 is corresponding to -2 in this as a surplus, right, for the labor. So the slab variable is not in basic, and therefore is 0, right? It's not in basis, and therefore is 0. X2 for the primer was 4, right? But when you come to the dual, X2 is actually the surplus S2 prime, all right, not in basis, right, or not in the solution, therefore is 0. You see, and you see the S1, which is -1, now becoming equal to. So S1 that was -1 is now equal to Y1, right, which is positive. And S2, which was -half, is now becoming half Y2, in the solution basis of the dual. So it can also be observed from the primer that both have the same Z, the same function, right? See, so from the weak duality theorem, right? So we have the weak duality theorem, right? From the weak duality theorem, the objective function value is the upper bound to the objective function of the primer problem, right? Similarly, the objective function value of the primer is a lower bound to the objective function of the dual. So this is what we want to see. So assuming we have this, we are representing this graphically, right? And we plot that. Okay, so what we are saying is that the weak duality theorem, right, for the objective function of the primer, remember the primer is max, right? So the value is outside the origin. Okay, the value is outside the origin. So the objective function is actually around this area, outside of the origin, right? And we see that it forms the upper bound of the primer, right? However, when you look at the dual, which is minimization, then it's also formed somewhere here. That is the lower bound of the objective function. Okay, so that's why we conclude to say that the optimal solution to both the primer and the dual are feasible than the objective function values of the primer and dual are equal, right? So if they are feasible, if you can solve both, then we say that the Z for the primer, right, is equal to the ZD for the dual, right? And this is what we refer to as the strong duality theorem. The strong duality theorem. So if they are not feasible, then we'll say that there is a weak duality theorem here. Okay, so there are some few assumptions here. So the previous considerations on the primer-dual relationship have bordered on maximization and minimization with these constraints, right? So this is not always the case, as there are situations, where we can have mixed constraints. So when we have mixed constraints, how do we obtain the dual form? When we have mixed constraints, how do we obtain the dual form? So we want to maximize Z, Ci, C1x1 plus C2x2, right? And it's subject to this constraint, right? So you see that the first constraint is an equal sign, right? It's an equal sign. What that means is usually A11x1 plus A12x2, right? We can say that it is less than or equal to B1, right? And again, A11x1 plus A12x2 can also be greater than or equal to B1. So that means that for us to go ahead to create the dual form of this problem with an equality constraint, right, we need to break the equality constraint into two. to have less than or equal to constraints and also greater than or equal to constraint. Because it's maximization, then we need to convert this into the normal form, right? Into the normal form of maximization problem. So we multiply through by -1, right? Then we'll be able to get that. So that we can have two constraints before the third constraint, and therefore we can have this as our new primer, right? This as our new primer before we go ahead to create the minimization form of the dual. So here we will say that we are minimizing Z, right? And they are the BI. So we have B1, B1, and B2, and it's Y. So Y1, Y2, Y3, and this, let me go this way to make it much neater. So this is a constraint 1, and this is a constraint 2, right? So minimize Z, P, right? The dual form is actually a B1, Y1, right? Minus B1, Y2, plus B2, Y3, right? And is subject to the first constraints, A11X1, then you change it, right? So it's A11Y1, Y1, plus, but because it's negative, so it becomes negative A11 Y2, right? And plus A21 Y3, and is minimization, so greater than or equal to C1, right? Then the second constraint is A12 Y1 minus A12 Y2 plus A22 Y3 greater or equal to C2. So this is supposed to C2. Supposed to be C2. All right, then Y1, Y2, Y3 greater than or equal to that. So you can see something comes to mind, right? Something comes to mind from this expression, right? AY, so we can always group this. We can always group that, right? And take our A11 out, take A12 out, right? And when you do that, you see that now you are having Y1, Y2. So Y1, Y2, right, is telling us something in our the complications of a linear programming that we did. Yeah, unrestricted variable. So we have now seen where this comes from, the unrestricted variable, right? Unrestricted variable. So it means that this variable, where we said it can attain any value, positive and negative values, right? And all are also greater than 0. So this has already been discussed, right? We discussed this in our linear programming. So this is what we are saying. So the term x1 minus y1 minus y2, all right, which is this, is in the form of y1 plus unrestricted, right? This enables us to formulate the dual without transforming the original equality constraint. So we don't need to go through the transformation. But as soon as we see an equality constraint, then it means that the problem, which is the original problem, this original problem here, therefore y1 is for this region, right? Then we'll see that y1 is unrestricted, right? We don't need to break them into two and say unrestricted. So the dual form of the original primer is formulated by treating the equality constraint as that and letting y1 be an unrestricted variable, right? So we've solved our final becomes minimize z and a11 that and y1 is an unrestricted variable, right? So in general, any equality constraint I in the primary results in an unrestricted variable yi in the dual. So when the primal constrains an unrestricted variable xj, the duality constraint j is an equality. So it is the opposite, right? So assuming we have this as our primer and there is an indication of unrestricted value, then it means that when we create the dual form from any problem which has that equality, right, then it will surely be unrestricted, right? Let's take one example. So this is a typical example here. We want to maximize 3x1 plus 7x2 and is subject to this constraint. However, the second constraint, which is y2, so assuming y1, y2, and y3, right? The second constraint, y2, is equal to constraint or equality constraint. So what that means is that the y2 must become unrestricted in the dual form. When you formulate the dual form, it becomes unrestricted. So that's what it means. All right. So when you look at a constraint which is greater than or equal to constraint, right? So greater than or equal to constraint also alters the standard primal dual transformation, right? So in this case, the constraint is multiplied by -1 to convert it, right? So we are maximizing that, and we know that all as opposed to in a normal form, you're supposed to have less than or equal to, right? However, we have greater than or equal to here. So then we have to multiply to by -1 to be able to convert that before we do the duality, and we'll have that, right? So the same thing applies to minimization problem, right? Minimization problem always goes with the form of greater than or equal to constraints. So if we want to form the minimization, we have a minimization problem, right? And we are minimizing this function, right? So this is the normal form, which is correct, right? However, in this form, the constraint is less than or greater than, right? We need to transform this and say that -1 is greater than or equal to 10. Then we can use that to transform our dual and say that this is our y1, this is our y2, this equation is our y3, and we can create the dual as 16, which is that, 10, which is that, and it's negative now because of this, right? We multiply to by negative to be able to change the rule. Yeah, these are all something which are straightforward. So if you want to summarize the primal dual relationship, right, we'll be able to say that when it's a maximization CJ's xj function, it becomes a minimization, right? The constraint I become variables yi's, right? The variable xj become the constraints j. The less than or equal to constraint become greater than or equal to constraint. The constraint I, if it's an equalities, right, sign becomes unrestricted. And if it's unrestricted, becomes equality in the problem. All right, so this is this form of the duality, and we shall look at the sensitivity analysis in the next video. All right, thank you.